A ray, a ray of light going parallel to the principal axis after reflection must pass through the principal focus. So rule 1. Then you apply a second rule. A ray of light hitting the mirror at 90 after reflection must pass through the center of curvature. So this ray incident on the mirror at 90 and reflects along the same path. Okay. Now, the two reflected rays are getting more diverged as they move on. There is no way the two rays would meet in front of the mirror to give you a real image. Because of that, let's extend the rays at the opposite side of the object or at the back of the mirror where they appear to meet will give us a virtual image. So we extend backwardly the two rays. And this is the point where they appear to meet. Because of this, we need to extend the principal axis so that because the object and the image, Mommy, I'm coming in. The object and the image would always be on the
Please,
principal
Mr. Ed, yeah, your line is breaking.
Please, is it a general problem at your end?
Yes, please.
At Maria's end, I guess. Let me see. Maria, is it better?
I think mine is breaking here too.
It's still breaking a bit.
Hey. Maria, can you reconnect? Because if it's not a general problem, then I think it's a problem from your end. Okay.
Yes, please.
So this is where the two reflected rays appear to meet. Where they appear to meet will be the position for the image. Okay. So from what we have, we can draw the conclusion that one, the image is virtual. Virtual because it is formed at the opposite side of the mirror. All virtual images are erect or upright. So it is upright or erect. 3. Comparing the two, the image and then the object, you can see that the image is more enlarged. So image is magnified or enlarged. Then finally, image is formed at the back of the mirror, or image is formed at the opposite side of the object. At the back of the mirror. So these are the characteristics of the image formed when the object is placed between the pole of the mirror and the principal focus. And the first one we went to. Please, if you have any questions on this, quickly ask. Then we look at other positions. Alpha, Leonard, mute yourself. Okay. Now let's look at when the object is placed at principal focus F. What happens? When the object is placed at infinity, what happens? Okay, so let's first look at objects placed at F and at infinity. So objects at F. Then we look at anything convex. So the mirror must just have small aperture. Then the principal axis divides the mirror into two. You rule a vertical line to cater for reflection beyond the aperture of the mirror. And this is a concave mirror. Mamiya. Is it better?
Yes, please.
Okay. So we take into account R is equal to 2F. Very, very important. So we take our measurements. I'm using 10 centimeters. Now, when you don't get this right, it will affect your radar. So F is here. C is here. Joel! Joel, use your phone for me. So object is at F. So use the rules. A ray of light parallel to the principal axis after reflection must pass through F. So 1. A ray of light hitting the mirror at 90 after reflection must pass through C. So incident. Now from what we have, there is no way these two rays would ever meet, either in front or at the back. So let's extend the rays backwardly to see if they can possibly meet. They appear to be written here. Now it is wrong. The problem is from the parallel reflected incident ray I took. If you don't ensure that the line is actually so parallel to the principal axis, this is what happens. So when you are using this rule, please do it well. In order to prevent this, you must shorten the height of the object. So let's pick it again. Reduce the height, because if the height is reduced, then we can see it well. we can draw the parallel and or ray very well. So a ray of light parallel to the principal axis. Check at your end for me. Is the rule really parallel to the principal axis? Is it? Check for me. Is it? Visual judgment from your rooms. I'm assuming this must be directly parallel. The way to go about this is also that you measure the object height. And I'm having something around 5 centimeters. So measure 5 centimeters from here. So it's like good. And so you can use this as a guide to draw your parallel line. So when I pick the head of this, I also pick the head of this. And that can help me get a parallel ray to the principal axis. Okay, so that after reflection, it must pass through F. Then a ray of light hitting the mirror at 90. Reflect along the same path and then passes through C. So incident, reflection. Now what happens is that the rays will never meet in front, neither will they meet at the back, no matter how far you extend it. What it simply means is that the two rays are directly parallel to each other. Now, when rays, reflected rays, are parallel in nature, then it implies that the final image will be formed at infinity. Why will it be formed at infinity? Because the two reflected rays are parallel, the image will be formed at infinity. So the conclusion is that when an object is placed at F, when an object is placed at F, one image form is real. Why is it real? Real because look at it. If we extend these two rays, okay, to the other direction, now the conclusion is they will meet at infinity. And when they do meet at infinity, when you draw the image, let's assume this point is infinity. When they happen to meet at infinity, when you join, you get the rays intersecting at infinity, and the image formed is inverted over there. Now, an inverted image means that it is real. So because the two rays will meet at infinity, okay, supposing this is infinity, when you draw, the image will be inverted. Inverted implies that the image will be real. So image formed is real. Two, inverted. Now when you look at this, supposing even this point is infinity, when you compare the object to the image, you realize that the image will be so much enlarged. So image is magnified. Then the last characteristic is that it is formed at infinity. Formed at infinity. So whenever an object is placed at the principal focus, the image is formed at infinity. Image form is real. image form is inverted, and image is magnified. And this is based on the fact that in astronomical telescope, you see, we use the astronomical telescope to view objects at far end, okay, heavenly bodies. Because the object is at a far end, we consider those positioned at infinity. So when you pick the astronomical telescope to view the stars, the moon at those far end infinity, the image is formed at the principal focus of the lens or the mirror. Okay, and look at using the telescope to view the moon and then managing to capture the image at Earth. Okay, so the rule is that when an object is placed at infinity, image is formed at a focal point or principal focus. Inversely, when an object is placed at the focal point, the image is formed at infinity. So let's draw a ray diagram for an image placed at infinity. And then look at where, sorry, the object placed at infinity, and look at where the image will be formed. So we draw another mirror. A vertical line indicates the center. A vertical line at the back to cater for reflection beyond the aperture of the mirror. Let's draw the principal axis. It's a concave mirror. Well, let me change the markers. It isn't writing so well. Okay. So take your measurement up and see. Ten. So this is P. This is F. This is C. This is the full. Now, because infinity is a very far end, we cannot put an image at infinity. But what we can actually do to draw the conclusion that an object is at infinity, or the rays, okay, hitting the mirror are coming from infinity, is that whenever in Venn diagram, whenever two or more rays are parallel to each other, then it means they are from infinity. Just as, look at these two reflected rays, because they are parallel to one another, we get to the conclusion that the image will be formed at infinity. So whenever reflected rays are parallel, the conclusion is that they meet at infinity. Whenever incident rays are parallel, the conclusion is that they are coming from infinity. Class, are you with me? Hello, are you with me?
Yes, please.
Yes,
Good.
sir.
So to indicate that the incident ray or the object is at infinity, draw two or more parallel rays, and because they are parallel and then incidenting on the mirror, we conclude that the rays are coming from infinity. So whenever a ray of light passes through Earth, after reflection, the reflected ray must be parallel to the principal axis. Rho 1. So the reflected ray so incident reflection. Then a ray of light hitting the pole of the metal. Hitting the pole reflects at the same symmetry. Reflect at the same symmetry. Now, you see, so this is the incident, this is the reflection. Now, when this thing, look at where the two rays are intersecting over here. The point where they intersect must be at the principal focus if the measurement is taken very well. Indicating that when rays coming from infinity, meaning the object is at infinity. So when you take your measurements well and your rays very well, the reflected rays would meet at F to indicate that when you have an object placed at infinity, the image is formed at F. Let's describe the nature of this image. One, image form is real. All real images are inverted. Now, this image is diminished. What is diminished? Let me extend the principal axis and just even imagine that the principal, the infinity is just at this point. Any position behind C. So if you even assume infinity is at this end, then this rays, these two incident rays may be coming from a point like this. So there's the head of the object, meaning the two rays are coming from this object. Okay, these two rays are coming from this object. When you compare the object and the image, you realize that the object size is so large. Meanwhile, the image size is reduced. Even when we are imagining that infinity is just at this point. Now, the farther the object goes, the larger it becomes. Okay, so we can come to conclusion that image is diminished. Image is diminished. Or reduced. Then finally, we say that image is formed at F. So these two must actually be at your fingertips. When an object is placed at F, we have real image formed at infinity, inverted, the image is magnified, and then lastly, formed at infinity. Then, oppositely, when the object is placed at infinity, the image is formed at F, image is diminished, image is real, and inverted. These are explanations to object at F and infinity respectively. Please, if you have any question, quickly ask before we look at convex mirrors. Any question? Or if I should throw more light on any of the illustrations, you can request. Else we move on. Do we continue? Mamia,
Please, can you repeat on why the image is diminished from infinity? When the rays are from infinity, can you please repeat why it will be diminished?
okay,
Because there's no object to compare it to.
I illustrated, but okay, let's go through that again. So object placed at infinity. Let me clear the diagram, and then we draw a new diagram to illustrate what we are doing. Maria, there's an object to compare to. Let's draw a mirror. Infinity is an infinite distance. Very, very, very large distance. So this is the center. And so the principal axis. A vertical line to cater for reflections beyond the aperture of the mirror. And it's a concave mirror. So take your measurement F and C. And I'm using 10 centimeter, another 10 centimeter. So this is F, this is C. We are saying that object is placed at infinity. All that we know about infinity is that infinity is an infinite distance. A certain distance far, 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 far beyond C. Okay? We cannot draw or determine what we are terming as infinity. But in our ray diagram, how do we indicate that rays are coming from an object at infinity? The indication is that whenever you have two or more incident rays that are going parallel to each other, then the rays are coming from infinity. Mamia, are you okay?
Yes, please.
So the rule, we cannot draw an object and place it at infinity, because infinity we can't precisely tell where exactly. All that we know is that it's a very distant position, very, very distant position. But in ray diagrams, whenever you are drawing rays, incident rays, coming parallel to one another, then it means the rays are coming from infinity. Whenever you have two reflected rays that are going parallel to each other, then it means the image is formed at infinity. So these are the rules of the game. So I'm going to draw two rays that are parallel to each other. One is passing through F. A ray of light passing through F after reflection, we all know must be parallel to the principal axis. So I'm going to draw here. So this is something to indicate that Then a ray of light hitting the pole. And these two rays are parallel to one another. This is hitting the pole of the mirror. Must reflect at the same symmetry, meaning wherever this angle is, I need to have the same measured beam. I am estimating this angle. So you must estimate correctly. Now, when you do it well, you realize that the two, this is reflecting, this is another reflected, 1 and 2. The two reflected rays meet or intersect at this point. Where they intersect must be F. For the fact that these two rays are parallel means that we have rays coming from infinity. Implying that the object is positioned at infinity. And when an object is placed at infinity, the image must be formed at F. Now, Maria, supposing this is this distance. Supposing this distance, even this distance from the pole is what I'm considering as infinity, then it means that the ray incident is always coming from the object. The incident rays are always coming from the object. The foot of the object and the image is always on the principal axis. So, supposing this point is what I am describing as infinity, then it means these rays, two rays, must be coming from the head of the object. Now, Mamiya, look at the size of the object per my assumption, and then look at the size of the image. If I'm assuming this is the point I'm referring to as infinity, you realize that the object at that end very, very large. Meanwhile, the image point at F is smaller. Mommy, isn't it?
Yes, please.
So the application is that I said this principle is used in astronomical telescopes. Now, astronomical telescopes are used to view heavenly bodies like the moon, the stars. Okay. Now, whenever you use the astronomical telescope to view such heavenly bodies, the image is always formed at the principal focus of the mirror or the lens. So look at the size of the moon captured at the principal focus of the lens. Very, very small. Meanwhile, the moon, the stars, very, very large. Okay. So that's the explanation. Any other question from? So you must be able to draw this to explain the fact that when an object is at infinity, the image is formed at the principal focus. Okay, then when the object is at F, image is also formed at infinity, the vice versa. All right, so let's look at what pertains in convex mirrors. We've done, concave mirrors, by virtue of different position of the object, can give you different description of the image formed. So we've looked at when object is at infinity, when object is between infinity and C, when object is at C, when object is placed between C and F, when an object is placed at F, what happens? And when an object is between F and the pole, please, this must be at your fingertips. Okay, this description must be at your fingertips. Let's go through them. We have 1, 2, 3, 4, 5, and 6. When an object is placed at infinity, let's describe the nature of the image form. Mamiya 1. Object is at infinity. 1. Image is
Real.
Image is real. More views.
It is inverted.
It is inverted. Real, inverted,
Diminished.
diminished.
It
Image
is formed
formed
at
at
the focal point.
Form at the focal point. Okay. Okay. Now, object is between infinity and C, beyond C. Let's describe the nature of the image. If you forget this, a quick sketch can even help you. A quick sketch. Object is placed between infinity and C, meaning beyond C. So when I place the object here, it is between infinity and C. You can quickly use a ray diagram. A ray of light parallel to the principal axis, reflection must reflect and pass through. In case you forgot it. So incident reflecting, then a ray of light hitting the mirror at 90 reflect along the same axis, or reflect along the same direction, passes through the center of curvature. So incident reflecting, and the rays are reflected rays are intersected here. So let's describe the nature of the image form. The hand, quick one. Let's describe the nature of the image form here.
It is inverted.
Inverted.
It is real.
It is real.
It is formed between C and F.
Formed between C and F.
It is magnified.
Oh, sorry. Look at it well. This objective image. Is it magnified?
It's diminished.
Diminished. The image size is smaller than the object size. So that's it. Now, when object is placed at C, we've gone through this, When object is placed at C, what happens? Object is placed at C. Oh, Leonard and Co. Inverted. Image is inverted.
It is real.
It is real.
Image is formed at C.
Image is formed at C. It's a hand.
And the image size equals the object size.
Okay. All right. Right, Pavana, thank you. Image size equals object size. Thank you. So we've also gone through this. Then object is placed between C and F. Placed between C and F. Image is
real.
Image is real.
Inverted. And the image is
Inverted.
enlarged.
Image is enlarged or magnified. And lastly,
It is formed at between C and F.
No. No, it is formed beyond C. When you bring it here, image will be formed beyond C. When the object is here, image will be formed here. Look at it all. When object is beyond C, image is formed between C and F. When object is between C and F, image will be formed beyond C. So it's the opposite. You place the object here, image will be formed here. You place the object here, image will come here. So take note. Now, object is at F. Object is at F. Let's describe the nature of the image formed. Frida and Co talk. Caleb, KJC, Mami Adwa, Leonard, Christine, Calvin. Object is at F. Quick one, object
Image
is
is
at
formed
F.
at infinity.
So image is formed at infinity. Thank you. Image is formed at infinity. Let's not waste time. Object at F.
Image is real and inverted.
Image is real and inverted. And lastly,
It is magnified.
it's magnified. Now, objects between F and P. This, I'll only take one of you to answer, especially those of you who always want to be quiet. Let me bring one of you to spot to do the talking for me. And Rachel, object is between F and P. Object is between F and P. What will be the nature of the image formed? Rachel, don't waste time. 1. Oh, Rachel is wasting my time. Oh. Okay, somebody else. Anybody can answer. Between F and P.
Image is erect and virtual.
Image is erect or upright and virtual. Thank you.
It is formed at the back of the mirror.
It is formed at the back of the mirror.
Image is enlarged.
Image is enlarged or magnified. Thank you so much. So this, I said, these positions, different positions must be at your fingertips. So please, from the discussion, we realize that there is only one position where virtual image is formed by a concave mirror. And what is that position? There is only one position of object where a virtual image can be formed in a concave mirror. And what is that position? What is that
When
position?
it is between F and P.
So take note of this. Apart from all other positions, okay, all other positions, okay, along the principal axis would give you a real image apart from the place between F and P. So this is the only situation where a virtual image can be formed by a concave mirror. Take note. Convex. Convex, or what's the other name for convex mirror? Convex or
Divergent.
diverging mirror. Please take note of this technology because sometimes instead of mentioning concave and convex, which you are familiar with, we can decide to use the other name. So this one, the reflecting surface curves inwardly. Just a small aperture, and we can roll the vertical line to cater for reflection beyond the aperture. The principal axis, we divide the mirror into two equal parts. So P is here. Let's take our measurement. This is F. This is C. F is here. And C is here. And because they occur at the back of the mirror, it means these points are virtual. Now, in one instance, let's bring the object close to the mirror. So let's use the rule. A ray of light, please finish my statement. A ray of light, finish my statement for me. A ray of light, hey, Mamiya and Co. Finish my statement. A ray of light
passing through the principal axis of a reflection.
It's what I'm trying to draw passing through. A ray of light
Parallel to the principal axis.
yes. That's what after.
Passes through F.
No, appears to be diverted from Earth. You know, this one divergent ray. So the divergent ray appears to be diverted from Earth. So you need to trace the divergent ray from Earth. So this is the first rule. Then the second rule, a ray of light hitting the mirror at 90, Mamiya and Co. Respond. A ray of light hitting the mirror at 90.
A ray of light hitting the mirror at 90 degrees is reflected back at the same
And
ray.
and appears to pass through a point on the principal axis. And this point is the center of curvature. So incident reflected. Even if we extend the reflected ray, look at what happens. Let me expand this reflected ray. The two reflected rays, 1 and 2, are getting more diverse, meaning there is no possibility that they would when they meet in front, because as they travel, they get more widened up. So when you trace the rays at the back, where they appear to converge, will be the point where the image will be formed. So they appear, the black and then the red markers appear to converge here, and that is the point where the image will be formed. This image form is virtual, so let's use booking line to indicate the image. So let's describe the image form. One, image is, let's describe
Image
the
is
next.
upright.
Okay, image is upright or
Erect.
erect. Two.
Image is
Image
diminished.
is virtual.
Let's talk about image is virtual. Why is it virtual? Why is it virtual?
Because it is formed behind the mirror.
Thank you. Three. We are describing the image form. What's the third description?
It is diminished.
Image is smaller than the object.
Okay, so it is diminished. And then what is the fourth description of this image form?
It is formed between P and F.
So all formed behind the mirror or at the opposite side of the object. Okay.
Okay.
So formed behind the mirror or at the opposite side of the object. So this is one positioning of an object in front of the convex mirror. Let's send the object a bit far away from the mirror and see what happens. So let's play a diagram. So some people are and see. So I'm going to extend the principal axis so we can place the object far away from. So let's place the object this time around a bit at a far distance away from the mirror and use ray diagram. Leonard, are you there? Nathaniel, are you there? They are not here. Rachel, Frida,
Sir, please, I'm here.
okay. So let's use the rules. A ray of light traveling parallel to the principal axis after reflection must pass through a must appear to be diverted from F. So this is the diverted ray. But the diverted ray appears to be diverted from F. Then a ray of light hitting the pole. I want to vary the rules. Hitting the pole reflect at the same symmetry. So look at the symmetry. Please, here you must draw the angle well so that they are the same. If not, if they are not the same, then the application of the rule is wrong. Now look at the two reflected rays. This one and then this one. Do they look like meeting in front here? Class, do they look like meeting in front of the mirror? And so you have to extend the two reflected rays where they appear to meet at the back of the mirror would be the position for the image. And the two rays appear to meet at this point. And that is the position where the image will be formed. So let's describe this image. One, image form is, quick one, image form is
Virtual and upright.
so virtual and upright. Or erect. Three. What is the third description? The third description of the image.
It is diminished.
Image is diminished. Then lastly, opposite to the object. Okay. Ellen, use yourself. Opposite or formed behind the mirror. So, yes, we varied the position of the object distance, but we are getting the same description as when the object was just close to the mirror. Okay, so for a convex mirror, irrespective of the object position, the same description of the image will be obtained. If you like, place the object at infinity, whatever, you get the same thing. So for convex mirror, no matter the object position, the same characteristics of image will be formed. Image will always be virtual, upright, diminished, and formed close to the mirror. And this is the reason for which the car side view mirror and then the front view mirror there is the inscription that objects you see or objects seen in the mirror appears closer than they actually are. Meaning that in a convex mirror, the image position is always close to the mirror, no matter the position of the object. That is the reason there is that writing. That object seen in the mirror is always closer than they really are. Because the image is always formed between the pole and earth. And so image is always closer to the mirror than where the object is actually is. This is the reason. So for convex mirrors, we don't actually have much problem because no matter the object position, the description is always the same. We have issue when we are dealing with concave mirror because for concave mirror, different object positions would give you different image description. Please, is that okay? Class, is that okay?
Yes, please.
And these things must be at your fingertips, please. You must know. You must know. When I review, when we have to review this and you are not able to tell me, in fact, I will not spare you. All right. Okay, so let's look at the mirror formula. The mirror formula. There is another way of describing the nature of the image formed. There is another way of describing the nature of the image formed, but this time using a formula or mathematical relation, and that is the mirror formula. So fasten your seatbelt, okay, whilst I take you through the mirror formula. What is the mirror formula? The mirror formula is a mathematical expression that establishes the relationship between object distance u, image distance v, and focal length small letter f of the mirror. So it is a mathematical expression, okay, that relates or that establishes the relationship between object distance u, image distance v, and focal length f of a mirror. And this you have seen before. This is the mirror formula. We are going to derive 1 on f is equal to 1 on u plus 1 on v. I think reflection from the board. 1 on f is equal to 1 on u plus 1 on v, where f is equal to focal length, the distance between the pole and then the principal focus. U is equal to object distance. Let me change my marker. And V is equal to image distance. You were using this mathematical expression in JHS. Find change of subject. True or false? True or false?
True.
Yes. In fact, they borrowed it from we the physicists. Okay. So let's see how this mathematical expression is derived. To derive it, let me clean this. We are going to draw a ray diagram using a concave mirror. So I take my measurement F. This time I'll estimate C. I just want to, you can place the object anywhere, but I am choosing to, I want to reduce the aperture because ideally the mirror has a very small aperture. Once I have my vertical lines, I don't need to have a giant mirror. Objects placed beyond C. Go through the rules. A ray of light parallel to the principal axis reflects and passes through Earth. Incident reflection. I need another one. An object, a ray of light passing through Earth. After reflection must go parallel to the principal axis. Oh, shit. So this is a reflection. My marker. All right. So the two reflected rays are meeting like this. This is the image. Now this is the object. So H subscript O to indicate object height. To indicate object height. This is the image. So H, let me clear my C. C, I don't need it again. HI to indicate image height. From this point to the mirror, from the object to the mirror, this is the object distance, U. From the mirror to the image, this distance. This is the image distance, V. I want to label the points as I have here. So I'll indicate this point as A, B, this point as C, this is already F, E, this is J, this is already B, so P, and this point as H. Now, please pay attention. Oh, we are deriving the mirror formula. Let's identify similar triangles. So identify similar triangles. How do we identify similar triangles? Conditions for identifying similar triangles are that one, when triangles are similar, their interior angles are equal. So similar triangles have equal interior angles. Two, when triangles are equal, one is a scaled up or scaled down version of the other. So two, they are equal. They are scaled up or scaled down version of one another. Meaning when triangles are equal, one is either bigger or smaller than the other. Okay, so these are the indicators that would help us identify similar triangles. Now, when we look at triangle ABF, triangle ABF, this is similar to triangle FPG. FPG. Why are they similar triangles? I said when triangles are similar, they have equal interior angles. Look at this angle. This angle here, this is triangle ABF. This angle is equal to this angle. And what's the reason? Why is this equal to this angle? What mathematical rule?
This is vertically opposite.
Vertically opposite.
So, they are vertically opposite angles. Now this is 90. The angle here is 90. And the angle here is also 90. Those, I said, these are thin mirrors, as if they are vertical lines, as if it's just a vertical line. So this is 90, this is also 90. And they alternate. Then this angle here is also equal to this angle here. And what's the reason? On what basis or reason can we draw that conclusion? This angle is also equal to this angle. Are they vertically opposite angles? They are also alternate. So these are alternating angles. So we can draw the conclusion that ABC, ABF is similar to FPG because their interior angles are equal. Okay. Now, when triangles are equal or similar, the ratio of their sides must also be equal. When triangles are equal, let me add that to this. 3. Similar triangles, or when triangles are similar, are similar. Rashid, mute yourself. The ratio of their size, are the same or equal. That's the third rule. Here, what do we mean? You see, because ADF and FPG are similar triangles, when I take their size, equal size AB divided by the side of the other counterpart, PG, it must be equal to, when I take AF and divide by FP, and also equal to BF divided by FG. I will consider BF this time because I don't have much information there. So I only take the ratio of this side to this side and this side to this side. So AB over PG is equal to that. Okay. Now, first, what is AB? AB is the object height, H naught. So I have H naught over PG. What is PG? PG is equal to the image height. This length is equal to this length. PG is equal to CE. So this is HI. And equal to, what is AF? Please, I want you to tell me this. What is AF? We want to determine AF. Now, AF can be determined out of AP and FP. So, from the board, we can see that AP is equal to AF plus FP. Now, what is AP? What is AP? I want somebody to look at it and tell us what AP is. What is AP? Anybody, what is AP? Please, whatever you see, share with us. What do you think is AP?
Please, you.
Yes, AP is object distance. U. So this is U. It's equal to AF is what we are looking for. AF. So AF plus. What is FP? What is FP? Class, what is FP?
Please have you.
No. This F is the principal focus. So what is FP or PF? Oh, it is clear. FP is the distance from the principal focus to the pole. So what is FP or PF?
V minus HI.
You are thinking far. FP is the focal length, small letter f. So the distance from the pole to the principal focus is the focal length. So FP is the focal length, small letter f. Therefore, AF is equal to U minus F. So this is U minus F divided by P, which is F. This is equation 1. Please, is equation 1 clear? How we derive equation 1? All right. Let's also identify another similar triangle. So apart from ABF and FPG, let's identify another similar triangle or similar triangle. Yes. And so let's see. Can you help me identify another similar triangle or two other similar triangles? A volunteer, quick. A volunteer to help us identify two other similar triangles. Who is volunteering for us? Okay, time's sake. So when you look at the triangle CEF, CEF is also similar to triangle HP. FHP. Now, when two triangles are similar, their interior angles are equal. So we can deduce that this angle here is equal to this angle here. Vertically opposite reason. This angle at C is 90. This angle at C is also 90. This angle by alternate angles reason is also equal to this. And so when triangles are similar, one is a scaled up or scaled down version of this one another. This is smaller than this, or this is bigger than this. Then we apply the third reason. The ratio of their sides must be equal. So CE by HP must be equal to CF over FT. Please, are you okay, class? Can I continue? Now, what is CE? CE is image height, HI over HP. HP is also the object height because this distance is equal to this distance. So H naught. This is equal to CF. CF. What is CF? I want you to help me determine CF. Class, help me determine CF. This distance, CF. Who is volunteering to tell us? CF. Don't forget, CF is part of the bigger distance CP. So we have CP equal to CF plus FP. So what is CF? Nathaniel, what is CF? Mamiya and Co, hurry up. What is CF? Okay, so
Image distance.
Mamiya, look at it. What is CF? As part of CP. So get CP, what CP is, get FP, and then you can find CF. Leslie, Frida.
It's Vin minus X.
Exactly. Exactly. Do not be tired of analyzing situation and then sharing with me, please. So CF is V because CP is V. FP is F. So CF is V minus F over F. Equation 2. Very, very simple. Now, look at equation 1. Equation 1 is HO over HI. This is HI over HO. We want equation 2 to look like equation 1. So we invert this equation 2. So when I reciprocate this side, the left-hand side, to have H naught over HI, this will also be equal to F over V minus F. This is the same as the equation 2. We haven't changed it. Now, because we have made it look like equation 1, we can equate the right-hand side because the left-hand sides are equal. So U minus F over F is equal to F over V minus F. Please, is that understood? Class, I hope you don't have any problem with this. You are not even talking.
Please, we
Okay.
understand.
So talk for me. Now let's multiply, cross multiply. When we multiply this by this, we have U minus F times V minus F, which is equal to F squared. Let's expand the left-hand side. We have U times V, UV. This time is minus UF. F times this minus VF. Then minus F times this plus F squared is equal to F squared. The F squared will cancel out. And when we send the negatives to the other side of the equation, we have UV is equal to UF plus VF. Okay. Now we are going to divide each side of the equation by, so divide through by UVF. So we are going to divide through each term by UVF. So UV divided by UVF. I think the black marker will rather help. Is equal to UF divided by UVF plus VF divided by UVF. And once we are dividing through by the same term, it's as if we are doing nothing to the equation. It doesn't change the equation once the denominator is the same. So we have UV cancelling out UV, UF cancelling out U and F, VF cancelling out V and F. What is left? What is left is that we have 1 over F is equal to 1 over V plus 1 over U. Ladies and gentlemen, this is the mirror formula. This is the proof of the mirror formula, which I earlier gave you. A mathematical equation that establishes the relationship between object distance U, image distance V, and focal length F of the mirror. Mania.
Please,
Mami,
I wanted to
I
know.
can,
I
I can
wanted to
get
know
your
if
question.
we'll be asked to
Aha.
show
Yes,
the
I thought as much.
proof.
I
We'll be
thought
asked to
as
show the proof.
yes, you must know. But this is not difficult. It's all about identifying similar triangles. Okay, you use ray diagram to indicate, use any position of the object to indicate its image. And identify for you object distance, image distance, object height, image height. When you finish, identify similar triangles. What is the heads up for identifying similar triangles? Triangles are similar when their interior angles are the same, when one is a scaled up or scaled down version of the other. And when triangles are similar, the ratio of their sides must be equal. So you take the ratio of their corresponding sides, AB, okay, corresponding with AB of the other pair, not the similarity. So, Mamia, that's all. When you go through the blah, 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 it's not difficult. Are you okay?
Yes, please. Thank you.
So please spend time, class, I'm talking to all. Spend time to go through this, learn how to, it's fun. It's actually fun when you understand how it can be derived, and then, you try to help your colleagues. So, spend time to go through it and then derive it. It's not difficult. It's just that because you are doing it for the first time, you think it is so difficult to learn. I urge you, okay? So this is the mirror formula, and that's what we'll be using from next week to solving problems. So apart from using ray diagram, we can also use this to describe the nature of the image formed. Okay. Do I clean the board? Hello, do I clean the board? People are tired already. Leonard, I realized you were asking us at the time it's running at snail's pace.
Yes.
Yeah, it will not grow. It will not grow. So I'll manage to finish my task. All right. So 1 on F, okay, let me bring it down. 1 on F is equal to 1 on U plus 1 on V is the mirror formula. The mathematical relationship or expression that establishes the relationship between object distance U, image distance V, and focal length F of the mirror. Apart from using this, there's something you must also know, and that is linear magnification. Linear magnification. You were talking about linear magnification in GHS. You were also using this. As for this, you are using it in mathematics. Math. You see, once we describe the nature of the image, sometimes we say image is magnified, diminished, up, C. When an object is placed between T and F, and you use ray diagram, the image is magnified. This is H, O, this is HI. We have this distance giving us object distance U, and then this distance giving us image distance V. So if we are to express or indicate whether the image is magnified or diminished, okay, that is the whole essence of linear magnification. Now, before looking at linear magnification, let's look at what we call as transverse magnification. In transverse magnification, we are looking at the ratio between the object, the image height as against the object height. So transverse magnification looks at vertical height of image and object. So this is equal to HI over H naught. That is image height over object height. Then we also have what we call lateral magnification. Lateral magnification. By lateral magnification, we are looking at the ratio of the image distance from the mirror as against the object distance from the mirror. So lateral magnification is equal to image distance V over object distance U. Now, theory and practicals at the lab has said that transverse magnification is always equal to image magnification. And so when you equate lateral magnification, which is V over 2, to transverse magnification, which is HI over H naught, this ratio of the two gives us what we are having as linear magnification M. Linear magnification M. And here we are interested in the magnitude of linear magnification. So magnitude of linear magnification is given by either image distance over object distance, which is also equal to image height over object height. Now, why this magnitude or absolute value thing? Sometimes, by virtue of whether the image is real or virtual, there is a positive or negative sign attached to this. Okay, so by breaking this absolute value sign or magnitude double line, here we want to say that we are only interested in the number, not the sign attached to it. Okay, the reason for which we indicate that. Now, when an image is formed and the image is magnified, then it means that the magnitude of the linear magnification is greater than 1. So when a value is given and that value is greater than 1, then it means the image is magnified, such as what we have in this case. If absolute value of the linear magnification is less than 1, any value which is less than 1, it means the image is diminished, such as when we say the objects are beyond C, it gives a diminished image. And when the linear magnification M is equal to 1, then it means image size is equal to object size, such as when the object is placed at C. So class, this is the whole nitty-gritty of linear magnification. We'll be using this with the mirror formula in our question solving or problem solving. Please, any question? Okay, Camille. Camille, it's not about finally. We haven't gotten there yet. All right, so I think once we've managed to discuss up to this level. Okay, so Cardinal, this is what I was saying. When we talk about lateral transverse magnification, we are looking at the ratio of the object height to the image height to the object height. And when we talk about lateral magnification, it's a ratio of image distance V to object distance U. Now, theory and experiment has it that lateral magnification is equal to the transverse magnification. So equating this to this gives us what we are calling as linear magnification, denoted by small letter m. Okay, so linear magnification can be equated to either transverse magnification or lateral magnification. That is all that is being said here. Please, any more questions? All right. If you don't have any question, I think to satisfy Leonard's wish, this is where I draw the curtains on today's meeting. Please spend time to go over all that we have derived, okay? Because we'll be applying it next week. Spend time to do so and then master for me before we meet on Tuesday. All right. So until Tuesday, may the good Lord be with you. Take care and have a very good night. In fact, bye-bye.
You too, baby. Bye.
Okay.